Welcome back. Hope you're doing well. Let's go ahead and continue on discussing the inner product. Remember that last time we've seen some examples of vector spaces that have inner products defined on them. Namely, inner products could define things like norms and give us everything that we would like for distance in our space as well. And they also have very neat properties of their own. Namely, we talked about the Cauchy-Schwarz inequality, the parallelogram identity, and other sorts of things that come into play like Pythagorean theorem that happen whenever we can define an inner product on our vector space. Inner products are also very useful on vector spaces in order to make orthogonal vectors in our spaces. Orthogonal vectors, we already have a geometric understanding of from things like Rn. In particular, if we're looking at things like maybe just in terms of x and y axes here, then whenever we take a look at two vectors, we would say that those two vectors are orthogonal whenever they make a right angle with each other. It's another way of in some sense saying that the two vectors are faced perpendicularly from each other. The angle between them is 90 degrees. So for example, we might be looking at the vectors 1 and 1 as well as -1 and 1, these two vectors right here. The reason that we know that these two vectors are orthogonally geometrically speaking is that they make a right angle with each other. In higher dimensions, we would be a bit more specific. We would say that the plane containing these two vectors, right, looking at the plane that contains those two, in that plane, those two vectors make a right angle. So we would discuss it like that. Algebraically speaking, we can just say something like this. We could say that taking these two vectors, the dot product of these two vectors is going to be equal to, well, let's find out. The dot product, recall, is the product of the first plus the product of the second components. So if you get -1 plus 1 equals 0, we would expect for these two vectors to have a dot product of 0. Since the dot product is the inner product in R2 that we're familiar with, we say that V and W are going to be orthogonal to each other whenever the inner product of V and W equals 0. So when you take those two vectors and plug them into your inner product formula, you're going to get that these two things are 0. And indeed, that's exactly how we want to be defining this. In Rn, the way that this looks is that we say these two things are orthogonal whenever their dot product is equal to 0. But in general, we'll be able to extend this to abstract vector spaces by looking at this in general inner products and things like this. And we'll talk about that later on once we get to talking about the things that we'll be discussing later on this week, namely the Gram-Schmidt orthogonalization and other such applications as we continue to move forward and discussing how to make orthonormal bases for our vector spaces. But for now, we're going to stick to Rn and look at this as a kind of our launching point, our launching vector space for this new concept of orthogonality. Now, we can take two vectors to be orthogonal, but we can also say a vector is orthogonal to a non-empty set inside of Rn, and that's here in definition 2. The way that we're going to denote that is we're going to say that one side of this little orthogonal sign, that is this little set of what you might notice are perpendicular lines, that this vector is going to be perpendicular or orthogonal to this set Y if whenever you take an element inside of our set, any vector inside of here, and then take the dot product with x, you still get 0. And that this is true regardless of what element that you choose in there. An example of this might be if I draw a little picture of R3 here, is I might consider the plane z equals 0. So here is the plane z equals 0, or at least its part in the first octant in the place where x, y, and z are all positive and non-negative. Namely, here is the place where z equals 0. It is the xy plane. And then I can consider the vector 0, 0, 1 right up here. And I can ask the question, what is the nature of these two, this vector with this set? Is it true that these two things are orthogonal with each other? Well, let me take an arbitrary vector inside of the plane z equals 0. Well, the only thing that we know about this vector is that it has a z component of 0. So indeed, anything else it can be non-zero in. If we wanted to write a general formula for what vectors are inside of this plane, we could write it like this, x comma y comma 0. And we know this because this is a subspace of basis 2, and it has two generating elements, namely the x coordinate one or the x value 1, 1, 0, 0, that standard basis element, as well as the y standard basis element 0, 1, 0. Notice that 0, 0, 1 is the z component there. But all generating elements are stem from this form, and putting all of those together in a linear combination gives us a general vector like this. So when we take the dot product of these two things, let's take a look at what happens. We have x, y, 0 dot product with 0, 0, 1. And if we take the dot product of these two things, notice that we get 0 plus 0 plus 0. Indeed, these two vectors should always be orthogonal to each other. The idea here is that vectors inside of the xy plane, these are all going off in this direction, right? Either going maybe back and forth here out of the screen, or left and right on my screen. Whereas z goes up and down from my screen and is hence a right angle from each of those either two generating directions. But we didn't have to choose 0, 0, 1. We could have chosen the subspace generated by 0, 0, 1 as well. We could have chosen any vector on this line. Notice that the formula that I have here does not change if I remove 0, 0, 1 and I replace it with 0, 0, z. That is the subspace element, generic subspace element generated by 0, 0, 1. So we could also say that the set generated by 0, 0, 1, that is the line where x is 0 and y is 0, and z is some generic value. We could say that this whole set, this whole subspace, is orthogonal to the xy plane. And that's because we have two non-empty sets here, x and y. And for any two elements, one inside of x, one inside of y, their dot product is always equal to 0. So that gives us some examples to see what these sorts of definitions, how these operate, and what all these kinds of combinations can be for either a vector, a vector and a set, or two non-empty sets together. R3 is indeed rife with all of these sorts of examples. We could take lines inside of each of those spaces, for example, those where x and y are both 0, and we can look to see that that is orthogonal to the line where y and z are equal to 0. You might remember this to be the z-axis, and you may remember y equals z equals 0 to be the x-axis. And it makes sense that these two sets should be orthogonal to each other because these two are going off in different directions. We can also prove this algebraically. You can see here, if we have generic vectors v and w of this form, then their dot product is going to evaluate to be 0. We could also look at the line x equals y equals 0. That is exactly the z-axis, like we said before, and that's orthogonal to the plane z equals 0. We know this to be the xy plane. And we've gone through and shown what this proof looked like as well. Now, there are some lines that are not orthogonal to specific planes that may surprise us. And so we want to make sure that we're paying attention to this as well, because this is something that can thwart our geometric understanding of orthogonality, like this one. The line x equals y equals 0 is not orthogonal to the plane z equals 1. And let's take a look as to why. If we have that the line x equals y equals 0 is here, that's the z-axis. Z equals 1 is going to be not the xy plane, but the one right above it at a z height of 1. So it's going to be this plane right here. Now, the reason that these two things are not orthogonal to each other is that recall that vectors inside of this plane start from the origin and then have to reach up to go to that plane. So vectors here are indeed not going to be orthogonal to vectors like this. This is not a right angle. Even though it seems like we've just taken the plane z equals 0 and moved it up by 1, that does not give us right angles anymore because our vectors, whenever we write them, stem from the origin if their terminal points indeed are going to be traced out by these sets, by these equations here. We can also see this algebraically. The line x equals y equals 0 is the z-axis and has the vector 0, 0, 1 in it. But guess what else has 0, 0, 1 in it? The plane z equals 1. I could just set the other two coordinates to be 0. And if I take the dot product of 0, 0, 1 with itself, well, we see that this vector is not 0, and we know the dot product of any vector with itself is going to be strictly greater than 0 as long as the vector itself is non-zero. We can even check that using our dot product formula, and we see that the dot product is 1, which is not 0. So this is an example of two sets that are not orthogonal to each other, as well as the plane z equals 0 and the plane y equals 0. These two planes are not orthogonal to each other. But John, I thought that these two planes would be going off in different directions. Z equals 0, we know, is the xy plane. And y equals 0, we know, is the xz plane, the plane that's going to be stemming off in the x and z directions. If we want to draw this picture, then xz plane looks like it's going off right here. Right here's the x-axis and here's the z-axis. And then the xy plane instead goes off like this. So here are our two planes for this picture. And the question is, why are these not orthogonal? Because take a look. There is an intersection, a very non-trivial intersection between those two planes. That intersection is right here. It's this one. It's this guy. This guy right here is intersecting those two planes. That's the x-axis. The xy plane and the xz plane both have the x-axis in common. Well, if we are going to say that these two would be orthogonal to each other, then any element in here would have to take a dot product with any element in here to get 0. But why don't I just take something like 1, 0, 0? That vector is a generating element of the x-axis and indeed is a part of both of these planes. It's a part of both of these planes, and so we could choose it as a vector inside of z equals 0 and ask what is its dot product with another vector in the xz plane. How about we choose, I don't know, what about 1, 0, 0? They're both, that vector is in both of these spaces. Well, this is a non-zero element, so its dot product with itself will again be something non-zero. Then that shows that these two spaces are not orthogonal to each other. So it's good for us to have some basic understanding of what these things are, because we're about to be taking we're going to orthogonalize vectors by either breaking them up into certain projections or by looking at complements of these vectors, and we'll discuss what each of these words means as we move along. But this last example especially taught us something unique about orthogonality. Namely, if you're going to have two orthogonal sets with each other, their intersection has to be trivial. Namely, if you're going to have the intersection of them, either they are going to be disjoint or they are going to intersect to give us 0. I'll take back the fact that they are going to be quote unquote trivial. If these were subsets, for example, they would both contain the 0 vector. But since these are two orthogonal sets, it is possible they could be disjoint as well. So I'll take back what I said about these having trivial intersection. I'll instead say they either have empty intersection or they intersect exactly at the 0 vector. Now, the reason the 0 vector is okay is because if I take the dot product of the 0 vector with itself, I'm still going to get 0 for that dot product. So if you have a vector inside of x intersects 0, y, or x and y, then it has to be perpendicular with itself. And so it's okay if the vector is equal to 0 or if b is just 0 vector. That's the only time that would be fine. Now, in general, if you have that they're disjoint, you can't even find this vector to begin with. So that would mean that there is no intersection between x and y, hence this other part of this proposition here. Well, continuing on here, proposition 2, let's say that V is now no longer a set, but let's take a look at a subspace of Rn. And let's let S be a spanning set for V. So in some sense, we're going to take S to be the generating set, or maybe something a little more of this set for V. Then the thing that we're going to say is that we only need to check orthogonality for each element in order to check to see if a vector is going to be orthogonal to this subspace. The only thing that we need to check is that it's orthogonal to everything inside of our spanning set. So for example, whenever I have to check, okay, for example, we went back to that XY plane, right? XY plane was generated by 1, 0, 0 and 0, 1, 0. This is a spanning set of the XY plane, the plane Z equals 0. If we want to check that 0, 0, 1 is indeed going to be orthogonal to this plane, the only thing I really need to check is that it's orthogonal to each of these spanning elements, 1, 0, 0 and 0, 1, 0. If I do that, then I'm done. Because any other vector can be written as a linear combination of elements inside of that spanning set. So if that happens, then because the inner product is linear in each variable, we can break it apart. We can break apart x for any regardless of whatever vector v that we are choosing as a subspace of Rn. We can break it apart based off of sums and scalars to make this dot product look a little bit like this. Notice that we have broken apart V to be separated in each term to have its own dot product, and we have moved out the scalars A1 through AK as well. Well, if each of these is equal to 0, if each of the elements on the spanning set is equal to 0 when taking the dot product with X, then this whole thing is 0. Every term has a 0 factor. Because of that, we have that X and V are perpendicular to each other. So here's an example of that. The vector 1, 1, 1 is orthogonal to the plane spanned by the vectors W1 and W2, where W1 is given by 2, negative 3, 1, and W2 is given by 0, 1, negative 1. Now, I can't imagine this plane very well, but that's okay, because if I can just take the dot product of V with W1 and V with W2 and check to see both of those dot products are 0, then we're good to go. And in fact, if I take their dot products, I get 2 minus 3 plus 1. That gives us 0, or 0 plus 1 minus 1. And that's going to give me 0 as well. So the dot product of V with both of these vectors gives me 0. So this is an example of orthogonality between this vector and this subset. So R3 is a very good place to be looking because we can start getting vectors and subspaces from our discovery, from our looking through and seeing the geometry as well as the algebra of these spaces. Let's keep going here with these Rn examples to start talking about orthogonal complements of a set S. Let's take S to be a subset of Rn. It does not have to be a subspace. Let's take S to be a subset of Rn. And we're going to define the orthogonal complement of this set, and we'll call it S perp, to be the set of all vectors X that are orthogonal to S. So, for example, let's say that we wanted to take 1, 0, 0 perp inside of R3. 1, 0, 0 perp inside of R3, well, that's going to be the set of all vectors that are perpendicular to this set. Well, let's think about what vectors would work in here. We would have 0, 1, 0. We would have 0, 0, 1. We notice that these two vectors are both, when we take their dot product, when 1, 0, 0, that gives us 0. And we also notice they are linearly independent from each other. Okay. Notably, if I took a linear combination of vectors of this form, this would also be perpendicular to 1, 0, 0, thanks to a previous theorem that we had there before. So the subspace generated by these two vectors would also be orthogonal to S. Now, the question is this all? Are these the only vectors? Is it just the plane that's spanned by these two vectors? Well, let's say we found one more. Let's say we found another linearly independent element of this set S perp, all of the ones that are linearly independent from 1, 0, 0. Well, if we found one more, then we would have a basis of R3. That would mean that S perp is everything. Everything is orthogonal to 1, 0, 0. However, we know 1, 0, 0 is not orthogonal to itself. So we can't actually have another element inside of here. We can only have these two as our spanning elements. So indeed, this becomes what? The YZ plane? This becomes the YZ plane. All of the places where X is equal to 0. This ends up being the orthogonal complement of the vector 1, 0, 0. What we discussed here ends up showing that this theorem, but by this theorem here, is that S perp is indeed a subspace of Rn, right? So what are the things that we have to check for subspace? Let's go through and see that here to be a little bit more precise with it. So let's say, for example, remember that the subspace test needs two things. One, you need to show that it's non-empty, right? So one way that we'll do that is we'll ask the question, is the vector 0 in S perp? Well, if I take this vector 0 and take its dot product with anything inside of the set S, well, then I'm going to get 0. 0 dot product with anything is going to give me 0. So yes, 0 dot product with any vector X equals 0, and that's going to be true for all X in our set S, right? Now, what happens if I take a linear combination of vectors inside of S perp? Let's say that if, let's say we have maybe if X and Y are in S perp, then by definition, we're going to have that. Well, I've kind of used X up here, but I'll use X and Y here as well. I'll say then by definition for all vectors Z inside of S, X dot product of the Z is 0, as is the dot product of y and z. So this is what it means to be in S-perp by definition, is that for any vector inside of our set S, we have x dot z is 0 and y dot z is 0 as well. Then we can check to see what happens with alpha x plus beta y. Here, alpha and beta are scalars. If we're working in Rn, then those scalars are real numbers. Then taking this dot product with z, again, z being a generic element of the set S, well, we can use the trick again that says that the dot product is linear in each variable. So we can break this apart like alpha x dot z plus beta y dot z. And since both of these is equal to 0, both of these are equal to 0, we're going to get alpha times 0 plus beta times 0. So this dot product is 0. So the addition of these two things is also in S-perp. Any linear combination of x and y is also in there. So what this means is that this passes the subspace test. We have that S-perp is a subspace. Indeed, if I took the perp of S-perp, what I would have is a subspace of all of the things that whenever I take its inner product with S-perp, I get 0. That starts looking like we're kind of reversing the process again. This starts looking a little bit like span of S. Indeed, remember that the S-perp by definition would be the set of all vectors, and we'll say these are vectors x, such that for all z inside of S-perp, x dot product with z is equal to 0. In fact, I'll keep using the dot product notation here. So let me rewrite this to be x dot product with z to be equal to 0. Now, this is for z and S-perp. What do we know about vectors z and S-perp? If I take their dot product with things of elements inside of S, they're also equal to 0. This starts looking like we're reversing the process again. It starts looking like we're trying to get elements of x that are back in here. And indeed, after a little bit of toil, we can figure out that it's exactly the vectors inside of the span of S that give us S-perp. Now, why is it the span of S rather than just, say, the set S itself? Remember that S does not have to be a subspace. But here, in the first part, we saw that S-perp is a subspace. Well, guess what? This is S-perp. This is the perp of some other subspace. S-perp is itself a subspace, and we're taking the perp of it. That gives us a subspace. Well, so that means that whatever this is equal to needs to itself be a subspace. And the span of S ends up being the right choice. In some sense, it is the smallest subspace that contains S. So it is just the right size for what we are looking for here. Let's keep going with some other examples. If V is a subspace of Rn, well, then we can use the second part of theorem 1 to show that V perp is itself. The smallest subspace containing the subspace V is the subspace V, because V is itself a subspace. So no need to add anything else there. In this case, the intersection of V and V perp is exactly the 0 vector. And these two cannot be disjoint from one another now. And the reason is that every single subspace, and V perp are both subspaces, every single subspace contains 0. So the intersection has to be exactly 0, thanks to our previous theorem. If they're not disjoint, they both contain 0. So by our theorem on the previous slide, they hence must be equal to the set of 0. Now, something else interesting happens here, which is that the dimension of V plus the dimension of V perp gives us the entire dimension of the space Rn. We could see this with some of our examples over here, looking back at our R3 example, for instance, where we were looking at 1, 0, 0 perp. So if we take a look at that, and instead of thinking of it as just the element, but think of it as the subspace generated by that element, so all vectors of the form x, 0, 0, so getting this subspace, well, then 0, 1, 0 and 0, 0, 1 are both generating vectors for the subspace of x, 0, 0 perp. This is a subspace of dimension 1, while these two together are linearly independent. So the vector space that these generate a subspace of dimension 2. 1 plus 2 is 3. That's exactly the amount of vectors that we have here in R3. So this happens in general as well for any other type of vector space. The dimension of V plus the dimension of V perp is equal to the dimension of the entire space. Another way to connect this is back to our world of matrices. Let's take again V to be a row space of a matrix. You remember that we had this notion of that the rank of something is the dimension of the row space or its column space, whichever one we're using at the time. If V is the row space of a matrix, then it turns out that V perp is the null space of the same matrix. Now, this isn't a proof, but it is something that helps us understand it. It's just that we know the rank plus nullity theorem tells us that the dimension of the row space to the dimension of the null space should add up to equal n. So there's this kind of analog here with this sort of result in calculating these dimensions here. And indeed, for theorem 3, it turns out that these two things are both equal. So now we have some good theory on orthogonal complements. We have a lot of good examples to help us kind of push through these in terms of especially R3, but we can notice and imagine what these sorts of vector spaces might look like in R4, for example. Now we know that we could start potentially imagining vector spaces of dimension or subspaces of dimension 2 inside of R4, for example, and then take a look and ask what would V perp look like. And we can start trying to get some understanding behind this as well. So we can be moving this intuition beyond just R3 and into things like R4 as well. The notion here in terms of R3 is given here in this picture again. Here we can imagine this being z equals 0, but we don't have to imagine this to being z equals 0. We could instead imagine this to be maybe V perp is just some sort of line inside of some sort of n-dimensional space. Let's say this is Rn. And let's say that this is a V perp is something of dimension 1. Then what we can imagine this to be is something called a hyperplane. A hyperplane is a subspace of dimension equal to the dimension of your entire space minus 1. So we could imagine this to be a hyperplane of our space. Maybe this has dimension n minus 1. But it looks a little bit like a plane if you're looking at it from a squished distance, because if we were in R3, for example, it would just be something of dimension 2. And it would be its own little subspace. It would have its own space for us to be working with here. So this vector space V, if we take its orthogonal complement, we just get the line coming out of it. It's all of the things that make a right angle with that space. Okay. Now, the question is sometimes is how can we start finding orthogonal vectors? Let's say that we have a vector space that we're looking at, and we want to start finding vectors that are orthogonal to that. Then something that we might try and do is begin by looking at vectors that are outside of the vector space to begin with. Going back to our R3 example, if we have the xy plane, or z equals 0, as our subspace V, then we can start thinking, okay, what would be a orthogonal vector to this xy plane? And we might start looking at vectors like 1, 1, 1. I notice that this is not a vector that is inside of the xy plane because here z is not equal to 0. But I have to ask the question, is this going to be orthogonal to the xy plane? And after a little bit of inspection, I would realize no, it is not, because vectors like 1, 0, 0 are inside of the xy plane, and the dot product of this vector with 1, 1, 1 is not going to be 0. So the question is, how can I use this vector still? How can I still use the vector 1, 1, 1 to give me a orthogonal vector? And that is known as the orthogonal projection of the vector. What we're going to do is we're going to break apart this vector 1, 1, 1 into two pieces. One part is going to be in the plane, V, xy plane is our example here. And the other one is going to be inside of V perp. The other one is going to be our orthogonal vector that we will choose. Indeed, we can always do this for any vector V that is a subspace of Rn, and then any other vector that we might choose. Then this vector is uniquely represented in the following way. It's represented as the sum of a vector inside of our subspace, like the xy plane, for example, as well as a vector that is orthogonal to it, like O right here. Here's our picture of this. Let's take the vector x. We can imagine that this is 1, 1, 1, for example. And then we can imagine this to be the xy plane. Well, then this is going to break apart into two things. If this is the z equals 0 as our plane here, then there's going to be one. This can break apart into two vectors that both sum to give me x. One vector could be orthogonal to it. Maybe it's 0, 0, 1, and the other one could be inside of the plane z equals 0, like 1, 1, 0. Notice that if I add up these two vectors, I get the vector 1, 1, 1. And that the first vector is inside of the vector space v, the z equals 0, and the other one is completely orthogonal to anything inside of this vector space v. Notably, these two vectors are themselves orthogonal. So that's something that has to be true for starters. Now, it doesn't just have to be orthogonal to this vector. It has to be orthogonal to everything inside of v. And once we set that restriction aside, it turns out that this sum of 1, 1, 1 equals the sum of the vector inside of here plus 0, 0, 1, a vector inside of the orthogonal complement of this vector space. It turns out that this decomposition of the vector 1, 1, 1 is unique, meaning you can't break apart these vectors in any other way. This is the only way that you can have some vector inside of the vectors of the subspace v and another vector inside of the orthogonal complement. There's no other way to break these two apart. That's what this theorem is saying. So any vector can be broken apart uniquely as a way of being written in terms of v and v perp. All right, so this is going to be, P is going to be called the orthogonal projection of the vector x onto the subspace v. Notice that we can say the here because of the uniqueness of this decomposition for the vector x. So P is the orthogonal projection of this vector. Now, the orthogonal projection is really special. Let's go back to this picture for just a second. The orthogonal projection is special because whenever I take a look at the orthogonal projection of x onto P, I can ask the question, what is the closest that I can get between the terminal points of x and P? Where maybe P is not just the orthogonal projection, but maybe just some other vector inside of the plane V. So for example, I could take a vector like this one, maybe right through here. Well, it turns out that the orthogonal projection has another special property. There is no easier way to get from the vector subspace V to the vector x, meaning that the distance between x and P is the smallest it possibly can be if we're limiting ourselves to vectors inside of the vector space, the vector subspace V. Let me try and draw a better picture here, just for the sake of having a look at it. Let's take a vector like this one. Let's say that this one is going off in V. So let's call this one V. And this is just some element inside of our subspace V. And I can ask the question, what is the distance between this point and this point? Now, we can't really see it here thanks to our 2D rendition, but there is a lot of depth going on between this distance between this point and the terminal point of x. So you can think that there is a little triangle being built right here, right, where this is another right angle being formed. Well, this is the hypotenuse of that triangle. And because of this, the hypotenuse is going to have a longer length than either of its two sides. And here, the side, that's one of the sides here, is this dotted line that connects P and X, P being the orthogonal projection of this vector. The fact that this orthogonal projection is at a right angle to the vector O gives us a neat little proof idea. I won't say it's a complete proof. We haven't been extremely rigorous with it, but it does give us a nice push forward on why this vector P is the smallest, that's the closest possible to X inside of our subspace V. If we wanted to write that in terms of looking at distance, right? So the distance, of course, being the norm of X minus V, or x minus p, like given right here, then for any vector v that is not this orthogonal projection p, but is still inside of our subspace v, this distance is strictly greater than the distance that x has from the orthogonal projection. And that is going to be this distance right here. That's the smallest possible. Everything else, you can make a right triangle, and you can make this distance with the other vector, the one that is not the orthogonal projection, the hypotenuse of that right triangle, where one of its sides is the one going from x to p. This is a unique value, which is this value right here, and it is called the distance of the vector x to the subspace V. That is the distance between those two vectors. Notice, by the way, that x minus p actually has a name. It's the vector O. I could move it over, and that becomes that vector, and we have an addition of two vectors at that point here. So another way I could say is that this is just the length or the magnitude or the norm of the vector O. In this picture, in this example of what we were doing, this means that the distance between the vectors p and x is 1. In fact, that means that the distance from x to the xy plane is 1 as well. So we could also do orthogonal projection not only onto a vector subspace, but also onto a vector itself. So we could do the same decomposition here. And the reason that this works is that any vector that we choose, say y, for example, any vector that we choose generates a subspace on its own. So we could just take the same machinery that we had from the previous example and meld it onto here by using the fact that y is itself generating a subspace. Now, with all of that machinery dealt with, we get an orthogonal projection of the vector x onto the subspace generated by y. And since that subspace is one-dimensional, we know the vector p is indeed orthogonal, or is parallel to the vector y that we are projecting onto. And it is the sum of that vector with some orthogonal vector to the vector y. So you can see here with this picture that this projection p is some sort of scalar multiple of y, hence the parallelness of the two vectors. And then x is the sum of these two vectors p and o. Once again, it is unique thanks to the machinery that we were given from the more general work of this in subspaces. Now, the question is, how can we derive this formula? Because we know that it is not always the case that the dot product of any two vectors is going to be 0, even if we pick something that's not parallel to the vector y that we wish to project onto. So we've got this unique decomposition here of x equals p plus 0, and the question is, how are we going to find this dot product? Well, in order for us to do this, we're going to start by taking a general projection p, which is alpha of y, that is going in the direction of this orthogonal projection vector p. So it's going to be, we know it's going to be parallel to y, so it's going to be equal to alpha y. So we know two things, that this vector p plus the vector o, the orthogonal projection, is equal to x, and we know that the vector p is some scalar multiple of y. Okay? Well, we already know that if we take the dot product of the orthogonal vector in y, well, the vector O has to be orthogonal to y, so that dot product should be 0. In fact, we also know that we can write the vector O in a different way. Because x is equal to p minus O, we could write O as x minus p. Well, what is p? P is alpha y, so we could write it like this. And expanding that out, using the linearity of the dot product, we get this sort of expression here. By the way, we know everything in here except for alpha. X and y are both vectors that are given to us. What that means is that we can solve for alpha. If we solve for alpha, we get that alpha is the dot product of x and y divided by the dot product of y with itself. Plugging back in what alpha is in terms for p, then we can solve for what p is equal to with a given formula. You may know this as the vector projection of one vector x onto another vector y. This is sometimes talked about in, usually in 2-dimensional or 3-dimensional vector beginnings. Used sometimes in a calculus course, sometimes before or after. But this is useful because this helps us answer this problem. Let's see if we can find the distance from the point x equals 3, 1 to the line spanned by y equals to -1. So the picture here is that we have a line that is spanned by the vector 2, -1, something like this. And we have the point 3, 1, 1, 2, 3, 1, something like this. And we would like to find the distance here that connects these 2 points, or rather this point and this line. And that's going to be this distance right here. That's going to be this distance that is the difference between this point and some point on this line, namely the orthogonal projection of this point onto this line. Well, we already know how to find the orthogonal projection, and so that should be our first goal, is to go through and find this orthogonal projection. Once we find this orthogonal projection, we can solve for what O is equal to, And if we find the length of O, well, then that's the length of this vector right here. So that's exactly what we're going to do. We start by finding the orthogonal projection of the vector x onto the line spanned by y. That gives us the vector, well, 2, -1. Oh, that's excellent. It's just the vector y itself. Then we go through and solve for O, and so that gives us the vector 1, 2, once we subtract 3, 1 from, or 2, -1 from 3, 1. And then if we take the square root of the squares of the components, we get square root of 1 squared plus 2 squared. This gives us square root of 5. We could also use this to find the point on the line y equals -x that is closest to the point 3, 4. Once again, our picture here is very similar, although not identical, to the previous picture that we had. This time, though, instead of trying to find a distance, we want to find a point. And that point is the point on this line that's closest to it. Well, we know that point on the line that's closest to it is going to be the orthogonal projection. That was because of a theorem that we had a couple of slides ago that says the distance between a point and a line is given by the orthogonal projection and its distance from the point. So if we want to find the point itself, then we're just looking for the orthogonal projection of this vector 3, 4 onto the vector 1, -1. Notice that we're using this vector right here because this vector is the one that spans the line y equals -x. We need a vector of some sort. And in fact, it really doesn't matter if I had chosen 1, -1 or 2, -2 or -1 and 1. Any vector there would do. But because I need that vector, I'm going to be subbing in 1, -1 for this spanning element of this subspace here. And once I go through and do that, I'm going to get the vector -1/2, 1/2. And that means that the distance between this point and this point is the smallest possible between all points on the line y equals x. So that will do it for us today. We've discussed a little bit about how orthogonal complements and projections can be useful in helping us solve problems in terms of Rn. In particular, they help us know notions of distance as well as geometry between these subspaces and vectors here. So thank you so much. Have a wonderful day.